So next we're going to talk about finding the moment of inertia of a cylinder about its transverse axis. So we talked about if the cylinder is rotating about its kind of center axis, but what if it's rotating about its transverse axis here? So that would be an axis right here through the center. And now when we do this problem, we have to think about a small differential mass and what the distance of that mass would be from this axis through the center. So let's think about our differential mass here. And if we draw it, again, pull this, make it a little bit bigger, it's going to have some radius r here. That's maybe our lowercase r. And some angle theta, and some distance L from this axis. And if we imagine this in a really, really small differential case, like it's almost this little rectangular prism with side lengths dl, dr theta, or r d theta, and dr. Okay? So now, okay, let's go back to our moment equation. The moment of inertia is going to be some r squared dm, and now this r squared is the distance to the axis of rotation squared. So in this case, it's not this generic r, is not specifically this radius direction in this case. In this case, the distance of this segment of mass from the axis is going to be this length L in one direction, and then in the other direction, it's going to be like in the x direction parallel to the axis. We don't care about that, but we do care about this direction here, right? How high is it off away from this plane, right? And so that would, like if you could imagine up here, obviously that's going to have a contribution that's related to the radius. Okay, so the expression then for the distance squared from the axis of rotation is going to be an L squared plus R squared sine squared theta. So this is our R sine theta squared and our L squared. Add those together. All right, and so now let's find our differential mass. We can see that the differential mass is going to be proportional to the differential volume since it's constant density, and the volume of a cylinder is L pi R squared. And now the volume of our little differential element is just going to be all of these side lengths. So we've got our dl, r d theta from that arc length in the infinitesimally small case, and then our dr. Okay, so now putting it together, so we take this part, put it in the r squared part, we take our differential mass part here, and then we make sure we get our limits of integration right. So for the L term, we're going to be going from negative L over 2 to L over 2. For R, we're going to be going from 0 to R. For theta, we're going to be going from 0 to 2 pi. Or it's also fine to go from negative pi to positive pi. It doesn't matter. Okay, so let's pull out the constants and do the L integral first. And the reason I picked that is because I thought that would be the easiest one, and I wanted to get rid of these limits of integration. So, okay, so now we've got, in this term, we've got an L squared, and there's no other L's here. So we'll do L squared becomes L cubed divided by 3. And now once we put in our L over 2 in that, we'll have a L cubed minus that half cubed. And then there's 2 of them because we'll have a positive 1 minus a negative 1. So then there's just 2 of them. And now for this term, we're still going to integrate this over L, and there's no L here. So we just have L times, and now I moved this R into this, so I made this R cubed, and I put all of the constants on the outside. We have our sine squared term, and we have 2 left to do. So let's do R next, because that also looks fairly easy. So we have our R term here, dr, so that's going to become r squared over 2. So here's our r squared over 2. And everything else is going to stay the same. And now for this term here, now we have an r to the third power. So we're going to make that an r to the fourth power and divide by 4. So here we go. And then in this case, like, it's pretty easy when we're subtracting a 0, so we don't have to remember anything complicated for that. And we just keep through that sine squared. And all we have left is our d theta term. Okay? And now let's take this theta integral of this term. And there's no theta in this term, so it's just 2 pi. Since we go from 0 to 2 pi, or if we went from negative pi to pi, it would also be 2 pi. And then this term, you might not know this, but I just looked it up. The integral of sine squared theta d theta is from 0 to 2 pi is going to be pi. So I'll put my 2 pi in here, start canceling stuff out, and my pi here, start canceling stuff out. And then that leaves us with ml squared over 12 plus mr squared over 4. Now you might look up different approaches to this problem, and there's other ones out there, right? Like I think sometimes in the book, like they look at differential parallel axis theorem pieces, and there's lots of correct ways of finding the moment of inertia about the cylinder rotating about a transverse axis, but I wanted to go over this sort of first principles approach so that you can use it in your homework if you need it, and if you wanted to just another practice with this type of integration. Thank you.